Okay, hello everyone. Uh, Welcome to today's lecture. I have shared my screen, and if you have any problem in seeing my slides, so let me know. Uh, so last time we were talking about IPC. Remember our discussion about processes was like processes they need to communicate with each other in terms and in context of IPC, and there are two main mechanisms for communication through shared memory and through message passing. So we had an example of shared memory communication to solve the producer consumer problem, right? Where producer and consumer they were sharing a buffer, memory buffer to implement an area to hold items and also pointers to put items in the buffer and to extract items from the buffer, right? And then we started talking about IPC using message passing, right? And we said that for that purpose, uh, uh, there are two mechanisms how sender process can receive processes from can receive messages from a process. And the first mechanism was direct communication, and by direct communication, which we covered last time. So it was like both the sender and receiver, uh, they need to know the process ID of each other. Like so in symmetric, indirect and symmetric communication, what we need to do is that sender needs to know the ID of the receiving process, and receiver needs to know the ID of the sender process, right? And then we said that there is also an asymmetric version of the direct communication where only sender needs to know the ID of the receiving process, but receiving process doesn't need to know the ID of the sender, so it can actually receive messages from other processes, and then it can look at the ID of the sender and decide whether to process the received message or not, right? So, but the problem with that direct communication approach was like, since at least sender needs to know the process ID of the receiver, so every time you run your application, these process IDs are updated. So maybe the process IDs which you have used to encode your application, they are maybe applicable on the first run, but then they will not be applicable on the second run, right? So that's why we said that indirect communication is also an option which actually solves the problem. So in indirect communication, what we do is that the messages are sent by the sender to a mailbox, and then receiver receives those messages by reading them or picking them from the mailbox, right? And then the two processes they have a communication link only if they have a shared mailbox, which means that they can exchange the messages only if they have access to to the common shared mailbox. Otherwise, they cannot do the communication, right? Also, there can be examples where two processes they can have more than one links, which basically mean that they share more than they share more than one mailbox. Why? Maybe they for two-way communication, like one mailbox was sending messages from the sender from process A to the process B, and the other mailbox to send the messages from process B to the process A. And similarly, another situation where multiple links can be needed is like where you need to prioritize the messages. So you have two different mailbox, one for the messages with regular priority and one for the messages with relatively high priority, right? Uh, Also, a link may be associated with more than two processes, which basically mean that a mailbox can be shared among more than two processes, right? Uh, and so that was the point where we left our discussion last time, right? So now let's continue and have a look at more details or features of message passing communication. And actually, we will also see a practical example or a concrete example where two processes they communicate by sending messages to each other when they are run on the Linux operating system, right? So before I continue, are there any questions related to the recap, this brief recap that I provided? Any questions about slides from the last week or last lecture? No? Okay. So we said that actually in indirect communication, both sender and receiver, they share a common mailbox. And then the question is that who is responsible for creating, deleting, and sending messages, and also for maintaining the creating, deleting, and maintaining the mailbox. Uh, so which basically takes us to the question that who owns the mailbox, right? So there are two options. One option is that we set our user process and then owner of the mailbox. The other option is that we can make the operating system as owner of the mailbox. So if a user process uh, is the owner, then it is actually the process that creates the mailbox, which is set as the owner of the mailbox, right? And then the mailbox is created in its own address space. So the owner basically can only receive the messages. So let's say if process A creates the mailbox, so process A is then the owner of the mailbox and it can only receive the messages. However, user can be any other process which can only send messages to the mailbox. So basically, owner can only receive the messages and user can only send the messages, right? Uh, Now, when there is a situation that when owner, that is the receiver, or the our creator of the mailbox, when it terminates, then the mailbox should be disappeared. Why? Because mailbox is the property of the owner or creating process, the process that created the mailbox, right? So if that happens, then it's mean that we need to notify the senders that the mailbox doesn't exist anymore and they should not be sending messages to that mailbox, right? The other option is that we can make operating system as the owner of the mailbox, right? So it which basically mean that the mailbox will now exist independent of processes. So which basically mean that the processes which are using the mailbox for sending or receiving, even if they are terminated, the mailbox will still exist there, right? So who will be the owner of the mailbox? Uh, so operating system is responsible basically for maintaining, so the mailbox is created within the kernel space. However, the process which makes a request to create the mailbox is set as the owner of the mailbox. And how it makes a request? By making a system call, right? We will see an example where we will actually do that, right? So when the creating process, if it terminates or it completes its execution, then what happens to the what happens to the mailbox, right? In that case, OS can possibly transfer the ownership to other processes, which are still using the mailbox, right? And also it is possible that we have multiple receiver that is owners over the time for the same mailbox. Let's say process A created the mailbox, but the mailbox is created in the kernel space, and process A uses the mailbox to receive the messages from process B. So process B is essentially a sender, which sender are user of the mailbox, right? So if the process A terminates now, uh, then maybe the kernel can make process C and C as owner of the mailbox to receive, so that process C can use the same mailbox to receive messages from process B, which basically mean that it is possible for a mailbox to have different owners at different time, right? Uh, Depending upon the situation or how the mailbox is used, which is not possible when we say that the mailbox is created in the in the user space and the process is responsible for owning it, right? Okay. So, any questions here?
Seems
Okay,
to
we
make
said
sense.
that. Yeah, go ahead. Go ahead.
Or it just seems to make sense.
Okay, thank you. So, we said that a sender process and a receiver process, they need to in like indirect communication, they need to share a mailbox, right? So then you can ask a question like what happens if, for example, if sender it cannot send the message immediately. For example, there can be situations where sender cannot send the message immediately. For example, let's say your mailbox is full, right? uh, or what happens if a receiver cannot receive the message immediately. So for example, receiver tries to read a mail from the mailbox, but the mailbox is empty. So then what should be the behavior of the receiver in that case? Or similarly, what should be the behavior of the sender when it tries to send a message, put a message in the mailbox and the mailbox is full? So there are like, when we say what should be the behavior, it means like should sender wait until space becomes available in the mailbox and then it can place its message, and only then it can continue with its execution, or should it like not be blocked, right? So it depends upon answering this question depends upon answer to our answer to another question, which is basically, can communicating process overlap communication with the computation? So which basically mean like uh, okay, so let me go back to the to OneNote, and let me try to explain what we mean by overlapping communication with computation, right? uh, Sorry. So week 7, day 1, right? Why I have all these notations here? I don't understand. Okay. Anyway, you can focus on blue color. Okay. So let's say you have a process, right? And it does some computation here, and then it want to send a message. Let's say this is process B, process A, and then it want to send a message to process B, right? Send message to B, right? Maybe I'm not writing the parameters in the correct order. So, but you get the idea, right? And then it has some instructions here which do some computation, right? Now, there can be two scenarios. One scenario is like these instructions after the send system call. So these instructions, they actually their execution is dependent uh, upon successfully sending the message, right? So if that is the case, then it's mean that we cannot overlap this computation with the with sending of the message, which basically mean we need to wait until the message is sent successfully before we can continue with these instructions after the send system call, right? Or maybe the other thing is like, let's say you have allocated you are running them as a separate thread, let's say thread 1, right? You are sending this part of code as you have allocated it into thread 1, this functionality and body of the thread 1. When we will move to the thread topic back, you will see how we can execute the code in body of a thread 1, right? And let's say this is your this send is executed by, let's say, thread 2. Now, if the code which is executed by thread 1 is dependent upon whether the thread 2 is successfully able to send the message or not, so then it's mean that thread 1 cannot continue execution until thread 2 has successfully sent, right? If it is dependent, right? So we cannot we cannot overlap. So this is computation here. The computation is performed by thread one, and thread two is responsible for doing the communication with the process B, right? So if there is a dependency, it's mean we cannot overlap the two things, computation and communication. But if there is no dependency, it's mean there is no overlap, right? Uh, so that is what we mean by uh, this question, that whether the communicating process, it can overlap the computation with the communication or not, right? So if it is not possible to do the overlap, uh, which basically mean that the computation after making the send system call is dependent upon successful completion of the send system call. So there is no overlap. So then it means is that our sender process, it must block until the message is received, right? Until the message is received by the receiver or it is placed in the mailbox, right? Uh, and receiver blocks until it receives a message is available. So now we need to look at the things from the perspective of both sender and the receiver. So I explained on one note using only from the context of the sender process. Same is true from the context of the receiver process. So for example, if a receiver process B is making a system call receive a message from the process A, and then it has some instructions following that system call. Again, the question is those subsequent instructions which represent the computation, are they dependent upon the successful receiving of the message or not? If they are dependent, we must wait. If they are not, we don't need to wait, right? So if we must wait, it's mean then there is no overlap. We cannot overlap them, right? So in that case, what happened that receiver will also block until it receives a message, right? A message is available. So this is known as blocking send and blocking receive. So blocking send is basically behavior where the function that invokes the send system call is blocked until the message is sent successfully. Okay. And blocking receive is the behavior where the process which makes the receive system call is blocked until it receives a message successfully. Okay. So, what is the advantage of this, of using the blocking send behavior and blocking receive behavior? We have easy synchronization between the sender and the receiver. Sorry guys, I will back. Just give me 1 minute. For the where were we? Okay. So what is like implication of this blocking send and receive? It leads to easy synchronization. What do we mean by easy synchronization? Easy synchronization mean like uh, sender sends a message and the receiver, it actually cannot continue until it receives that message, right? So similarly, so as a result, what happens that there is like there is uh, one-to-one mapping between the message which is sent and the message which is received, right? So because until a message is sent successfully, the sender cannot continue. And similarly, a receiver, until it has successfully received a message, it cannot continue, right? So the messages are like sent like in kind of in order, right? So like if sender is sending, let's say messages A, B, and C. So first it will send A and then B and then C. So receiver will receive them like A, B, and C, right? So uh, here is how you can actually use how you can use the send and receive system calls. So these are just like short code snippets but we will have a complete example at the end of the slides. Okay. So for example, what does the producer need to do? Again, let's say we are considering again the same producer and consumer problem, but not this time we are solving this problem using message passing instead of shared memory, right? So what does the producer need to do? It produces a message, and then what it does is that it sends the next produced message, right? It continuously keeps sending, and the on the other side, uh, our consumer, it makes the receive system call to receive the message and store it in this buffer, which is, so basically this is a buffer or memory which you have already allocated, right? So next command is a memory allocation of message type, right? And then you consume the item in the next consumed, and then you again receive the next message in the same memory and then consume it, right? And here on the producer side, you are producing an item in the next produced and then send it, right? Okay. Now, if we so we ask this question that can communicating process overlap communication with computation? So again, there are two possible options. Depending upon the situation where there is no overlap, we will use blocking send and blocking receive, right? But if it is possible to do the overlap, which basically mean that the computation, the instructions representing computation after a send or receive, they are not that those instructions are not dependent upon the successful completion of the sender receive, then it's mean that our sender receiver don't need to wait. So what a receiver can do, so that sender can send the message uh, uh, or so it can send the message and then two things can happen, right? So one is like the message is sent successfully. So for example, there is a space available in the mailbox, right? Or we make the send system call and it returns us a failure because maybe the mailbox is full, right? However, in both cases, the control will immediately return back to the process which is making the send system call, right? So the block, so it will not be like that. The execution control is not returned back until it is a success, right? So and since the control is returned, we can check the return value of the send system call, whether it is success or failure. So if it is success, we can continue. If it is failure, we can maybe do some computation and then try the send system call after some time again, right? Hoping that in that time interval when we are waiting, the space becomes available in the mailbox and our next try will be successful. Similarly, on the receiver side, uh, because we can overlap the computation and communication, which basically means the computation is not dependent upon the previous successful reception of the message. So what can receiver do is that it can make a system call to receive the message, and again there will be two possible options. Either the message will be successfully received, or it will be a failure, null, right? So if it is a failure, we can check the value we can check the return value. If it is a failure, we can again try. But irrespective of whether the message is successfully received or it is a failure, the execution control will always be returned immediately to the user process, which is making the receive system call, right? So this behavior is known as non-blocking send and receive, right? So where the process which makes the send system call, it is not blocked. So it immediately gets back the return value, indicating the success or failure. But here in this case, the control is returned, execution control is returned to the sender or the receiver only if send is successful or receive is successful. Otherwise, the control is not returned until uh, until we achieve the success. Any questions? Okay. The other thing is like the other question which we can ask in reference to our original question, which was basically how sender or receiver behave if it cannot send or receive the messages immediately. The other question is like, is messaging queue shared among multiple senders or receivers, right? Uh, and can the message be buffered or not? So if if like our queue is shared among multiple senders, let's say multiple senders are trying to send the send the messages to the same mailbox, right? So it's mean that we need to control the access to the mailbox. So because it is possible that, let's say, process A and process B both are trying to send to the mailbox at the same time. So we need to control the access, which basically mean we need to synchronize the access of a mailbox by process A and process B. And also, the other question we need to think about is that what is the capacity of our buffer? Can the messages be buffered, or basically what is the size of our mailbox, right? So does it has capacity of holding the one message, or two messages, or what, or zero messages, right? So to answer this, can the message be buffered or not? There are two options or two possibilities. We can have a mailbox with a zero buffering capacity. If we say that the messages can be buffered or not. So if the messages cannot be buffered, it's mean that our mailbox has zero buffering capacity, right? So if that is the case, that our mailbox has no buffering capacity, then then the sender or the receiver, they will always use blocking send, right? Because since there is no buffering capacity, so sender cannot simply put the message in the mailbox and continue with rest of its program or rest of its execution, right? Because there is nothing to hold the message. So that's why it must wait until the receiver receives the message successfully, right? It must block. But if our mailbox has a capacity, has a non-zero capacity, then again there are two options. Like we have bounded buffer capacity, which mean that our mailbox is of finite size, and unbounded, where we practically our mailbox has like infinite capacity for practical purposes. Infinite mean that it is sufficiently big, sufficiently large, right? So if let's say we have bounded buffering capacity, so when message queue is full, then sender must be blocked, right? Because if message queue is not full, what the sender can do is that it can simply uh, make the system call to send the message in the mailbox, right? And then it can continue with the execution, because then the OS kernel can take care, the kernel can take care of that message, right? Once the message has received in the kernel space, now it is responsible and it is placed in the queue. Now the sender don't need to worry about it, because ultimately then it will be delivered to the receiver, right? But if our bounded buffer or our mailbox with the bounded capacity is full, then it's mean that the sender cannot place the message in the mailbox, right? So it cannot continue with the execution. So it's mean that in this case, the sender must be blocked. And if it is unbounded buffer capacity, then sender will never block, right? Because all the time, whenever it will try to send a message, we are saying that our mailbox is big enough to hold the messages. Any questions here about blocking, blocking send, blocking receive, non-blocking send, non-blocking receive? No? Okay. So here is the graphical depiction of like what we have discussed in previous couple of slides. So how sender and receiver communicate using message passing. So here by buffer we mean the mailbox, right? So but the buffer is maintained in the kernel space, right? It is not maintained in the user space, just like we saw in shared memory communication. So whenever sender wants to send a message, it make a system call, and as a result of that system call, the message is placed in the buffer. And whenever receiver needs to receive a message, it again makes a system call, and as a result of that, a message is made available from buffer to the receiver, right? It is picked from the buffer or from the mailbox to the receiver, right? Now, uh, based uh, on the choices of buffer and based on the choices of the type of the send and receive, we can have different combinations, right? So what are the choices we have in terms of the buffer size? Like we have zero buffer, or we have some buffering capacity, right? Some finite buffering capacity. And what choices we have in terms of behavior of the send and receive: blocking send, blocking receive, non-blocking send, and non-blocking receive, right? So let's see that what happens under each combination of buffer size and the behavior of the send and receive system calls. So when we have blocking send and we have a mailbox with zero capacity, so what we need to do is that sender, it must wait until receiver receives the message, right? Because there is no buffer. So if there is no buffer, the message must be received by the receiver here, right? So until it is received by the receiver, our sender cannot continue with the rest of its execution. However, if we have some buffer, then and sender is making the blocking send, so then it waits until kernel receives the message, not the receiver process, right? So what does it mean by kernel receives the message? It means that the kernel has placed the message in the mailbox or in the buffer, right? So if buffer has space, then there will be no wait, right? So this is the behavior of the block. So the the sender will wait until the message receives the kernel receives the message, right? Because we are saying that our buffer has a non-zero capacity and it is not full, right? If buffer has some space. Okay, blocking receive. So what happens from the perspective of the receiver? So if we have zero buffer, then our receiving message, receiver process, it will wait until sender has a message, right? Because again, there is no possibility of storing the message in the mailbox because we have zero buffer. So until sender has a message, our receiver will wait. On and but in the so which basically mean that our receiver will not be able to continue with the computation or with the next instruction, right? So it will be blocked, and blocked until what time? Until sender has a message. On the other side, if we have some buffer and receiver is using the blocking receive system call, so it will wait until kernel has a message, right? So if the kernel has a message, then it will wait only until that time point, right? So even like, for example, sender is not sending any more messages, but there are messages placed already in the buffer. And so receiver will not wait for the sender to send new messages as long it can read from the kernel, right? Non-blocking send, and when we have zero buffer. So if the sender is using a non-blocking send system call and the buffer size is zero, then our sender, it will receive with receiver received the message or error, right? So here we are receiving, here we are returning in case of blocking send only when receiver successfully receives the message. Here we immediately return. Although we have zero buffer, we immediately return, and but return with the status value or return value, which tells us whether the receiver was able to successfully receive the message or not. If it was able to if it was not able to successfully receive the message, then sender can try sending it the same message again, right? On the side of receiver, uh, sorry, not on the side of receiver. When in the case where we have some non-zero capacity for the buffer, and sender is using the non-blocking send system call, so the call will return with kernel received the message or error. Note that's why I've used different color here. When it is zero buffer, so the non-blocking send will wait for the receiver to either receive the message or send an error, which basically means it will take more time. But if there is some buffer, then the non-blocking will send will receive either with the success or error, and success here mean that kernel has received the message or not, right? Which basically mean the message has been placed in buffer or not, right? But it will return immediately in both cases. It will not be blocked until this is the difference from this case. Like, where is this? Blocking send and some buffer. In blocking send and some buffer, we wait until kernel successfully receive the message. Here, we don't care whether the kernel successfully received the message or not. If it receives message successfully, we tell the sender that, okay, your message has been delivered. If not, we tell the sender that, okay, your message has not been delivered, so try it again. Okay, and non-blocking receive again, when we are using zero buffer, so it will return with the message or none, right? Uh, non-blocking receive, if you have zero buffer, so it's mean that the message cannot be stored. So the receiver message, sorry, the receiving process, it will return with a message or none, right? Uh, but and same is true when you have some buffer. The only difference is that when you don't have zero, but when you have zero buffer, receiver will receive the message from the sender, right? From the sender. But if you have uh, uh, some buffer available, so the message will be, it will receive the message from the buffer, or it will pick the message from the buffer, right? So in both cases, it will return immediately. Any questions? It will return immediately with the return value, telling whether it was successful in receiving the message or not. Any questions? Okay, so what if there would be an infinite buffer? So in that case, uh, what will be the behavior of sender? Will it block? Will there be a situation where it will get blocked, or will there be no such situation?
Let's see. I don't think it'll get blocked because, again, you have an infinite buffer, so you can keep pushing the messages into the buffer until they're ready to be received. Or am I
Uh,
understanding that wrong?
yeah, that is true. Sender will never block. What about receiver? Will there be a situation where receiver can get blocked when we have buffer of infinite size?
Uh, Receiver probably would block because if it's not ready to receive a new message, then it would have to block the next one, right?
Uh, what do you mean
No,
it is not ready? Do you mean it is not making a system call, or
maybe
so?
I'm not understanding that part.
Yeah, so think of the situation where you have a buffer of infinite size, but buffer is empty, right? So if the buffer is empty, and then if you are using blocking receive, then you will get blocked, right? This is the case here, right? If you are using the blocking receive, you have infinite buffer size. So you will wait until kernel has a message. But kernel can not have a message if the buffer is empty, right?
Okay. So
So
if that if you have no message, that's when you block it.
yeah, yeah, yeah. So, but if like you are using, let's say, blocking send, and you have infinite buffer size, so then there will be no case when you will have no space, right? We says if buffer has space, right? There will be
Right.
no case when the buffer has no space. So it's mean it can accommodate infinite number of messages, right? So if you use blocking send, you will never get blocked actually, because all the time you will be successful, right? And
hmm
even When you use non-blocking, you will not be blocked.
Right.
Okay, any questions? Someone has sent a message. Random question, but when will we get our exam backs? Okay. Uh, uh, the TA has made an announcement. Please go and check the announcement on the Canvas page. Okay. Okay. So here is a concrete example of how we can do the inter-process communication between two processes which are running on Unix-like system. For example, if you have Ubuntu installed, you can test this example by simply copy pasting everything there, right? But let's first try to understand, right? Uh, so here is the problem. Here is the situation. So we have a producer process and a consumer process. Producer sends messages to the consumer, right? And this is just a note or a caution that if you want to run this example, we definitely we have two processes, sender and consumer. So you need to first run the consumer process first, right? So you have two different C files or two different programs. So you just first need to launch the consumer and then the producer. Why? I will ask you to answer this question when we are done with the understanding of the code. Okay. Okay. Will our exam be released so we can see? Oh, okay. Let me first finish with the lecture slides, then I can take the questions regarding exams later on at the end of the lecture. Okay. Let me first complete the slides. Uh, okay. So we have here a header file. So in this header file, we are defining a macro, which is basically queue name, a name of a queue or name of basically your mailbox. So it can be anything. And I said like just a name, right? You can write anything, my name, my mailbox, your mailbox, whatever you want, right? And other than that, in the header file, we are defining a structure. And in that structure, we have two data members, ID of the message and a character string or a buffer of 64 bytes. So basically, we have a buffer where we can, by buffer, I mean we can store in each item a message of 64 bytes, of size of 64 byte, and then each message also will have its own ID, right? And that's it in the header file, right? Other than that, we have the code for the producer process. Let's say we have written it in producer.c file. Let me walk you through this. So here you are including a bunch of header files. And then in the main, you are first making a variable MQ message queue of type message queue descriptor, right? So, and then you are creating a variable to hold item of type item type. So this is just like this will be used to uh, hold your message which you want to send. So you will put the message in this item and then you will send this item to the sender, to the receiver, right? So n is a variable which we are going to just use to store the return of our return value of the send function call, send system call. After that, what we are doing is that we are opening the queue, right? So basically, it's mean that we are uh, making we are making the system call to get access to the mailbox. Okay. And for that, what we need to specify the name of the queue or name of the mailbox, and then here we need to specify the type of access we need. So we are requesting the access to allow read and write operations so that we can actually as a sender as a producer you need to only write, but here we are combining both read and write. Okay. So now, what we are doing that after making the system call MQ open, we are checking the return value. So if return value is equal to -1, it's mean that there was something wrong, and we failed in opening the mailbox, right? And then we exit. Uh, Otherwise, we declare a variable I and set it equal to 0. and then we enter an infinite loop. The producer enters an infinite loop. So here, remember we had already declared a variable of type item. So we are setting the ID equal to value of I, which is first 0. So ID of the first message will be 0. And then we are setting the message equal to OS is good. So we are simply copying string copy item.str uh, OS is good, right? So this is our message. And then we are sending the message by making the system call mqsend, right? And here what we need to first specify is the ID of the or the pointer of the uh, mailbox, right? Which is returned as a result of MQ open system call, right? And then after that, you need to specify the pointer to the message or pointer to the item which you want to send. So actually our message consists of two things, the ID and the string OS is good, right? And then you also need to specify the size of the message, which will be equal to size of struct item type. And then the last parameter is 0, which is basically the priority of the message. So we are setting it to 0. Again, in the end, we get the return value of the MQ sent and we check it. If it is equal to -1, it's mean that our send request failed and we exit the program. Otherwise, we increment I++ and we wait, put our process to sleep for 1 second. And when you go back to, when you wake up, you go back to again and you create another message. This time everything else is same, only you are changing the ID of the message. So first time it was 0, then 1, 2, then 2 and 3, but the string is same every time. OS is good. Okay. And then you will be in this infinite loop if everything goes successfully. If not, so then like if there is a case, like for example where you get out of the loop, so you close the mailbox and you return. Okay. So this is the code of the producer. Any question there? No? Let me check the time. Yeah, we have time. No worries. Okay, so here is the code for our consumer process. First, we are including a bunch of header files, and then in the main, we are again making a variable of message queue descriptor type. Then we are also getting the we are making a variable of type message queue attribute. So why we will use it to get the attribute of our message queue or the mailbox, right? And then again we have a pointer of type item type. Okay, so this is where which we will use to store the point to get the pointer of the received message. Other than that, we are declaring a bunch of other variables. We will see how they are used. uh, Variable n, buffer length, and buffer pointer. So the producer is sorry, the consumer is doing what? It is first uh, opening the mailbox. So we are again using the same system call, specifying the name of the mailbox, specifying the type of the access which is needed, read and write operation. And here we are also ORing it with an O create flag. So here, which basically it means that if the message queue doesn't or the mailbox doesn't exist already, create the mailbox, right? And then we are specifying another flag which specifies that, which basically mean that all users, they can read and write the queue but they cannot execute it. So execute it mean like the messages which are placed in the mailbox, they are only for and read, you can only read a message or write a message. You cannot consider that message as a code and execute it. Okay. And then null, I don't remember what is meaning of specifying null as the last parameter, but you can always go and check online what is meaning of like significance of the last parameter and what is how it is interpreted when we set it equal to null. Okay. uh, I can't recall it. Okay, so here we are basically saying, okay, open a mailbox, and if it doesn't exist already, so create the mailbox and then open it. And then here we are simply doing the error checking to find if we were successfully able to create the mailbox or not. If not, then we exit, right? And if we are able to successful, then we get the attributes of the mailbox, right? And we get the attributes uh, in this variable of type message queue attribute, which we have defined here, right? So what we can do is like by using this message queue attribute variable, we can actually get the maximum message size. Uh, so which basically is like how large what is the maximum size of a message which can be placed in the mailbox, right? So now what we are going is that we allocate large enough space for the buffer. So what we are setting here is that we are getting the uh, message size, a maximum message size, and setting it equal to buffer length. And then we are saying, okay, now allocate a buffer of the required size and return the pointer in buffer pointer. Why we are doing this? Because remember that, so if this is your queue, or if this is your mailbox, let's say, right, and receiver is, let's say this is receiver. So if receiver picks a message from here, then it needs to, let's say this was message M. So it needs to store this message into its own address space locally, right? So where will it store this M? It needs to allocate a local buffer. So where it can put the M, right? Pick it from the queue or the mailbox and put it in its local buffer R. So that's why we need to first know that what is the maximum size of the message which we can receive in this mailbox. And according to that, we dynamically allocate a buffer of the same size. So this is what we are doing here, right? Okay. So after the allocating this buffer, we are saying now we are entering an infinite loop, and the receiver makes, our consumer makes a receive system call. So where you specify that, okay, I want to receive the message from this mailbox MQ, for which we already received from successful execution of MQ open. Then you specify the pointer of the buffer where you want to put the message which you have received from the mailbox. So actually you are specifying the address of this buffer point, this buffer. You also specify the buffer length, the what is the size of the buffer, and null. So if not null, pointer to variable to separate receive message, pointer to variable to store priority of the, yeah, okay. So this is the case when you like assigning the priorities, also to the sender is assigning priorities to the messages which are sent. If that is the case, you will also receive and you will also need another buffer to store the priority of each message received. Okay. But in this case, remember, when on the sender side or on the producer side, we said that we are not using priority. Priority is 0, right? So we don't care about it. So we are not storing it anywhere. Uh, then we are actually doing the error checking to find if we were successfully able to receive the message or not. If not, we can exit. And if we are able to successfully receive the message, then what we can do is like we are printing this only for our own purpose to like do the error checking, right? So we are simply printing the message that MQ receives success, message size is this one, right? And we are then converting that message which is placed in this in this buffer here. We are converting it, or we are like doing the typecasting to item pointer, so that once we have casted, we can get the ID of the message, and print it. And we can also get the string in the message and print it as well, right? And then we free the buffer pointer, right? And so actually here your while loop is ending, right? So while loop is starting here and ending here. But if there is a case when you get out of the while loop, then you must free the buffer pointer, the memory which you have allocated here, this one, this memory, free this, and after that, close the mailbox, right? Detach yourself from the mailbox and then return 0. Okay. Any questions? Okay, if no questions now, can anybody tell me why I said that in the following example, run the consumer first? Anybody who want to respond? Can anybody tell like
Can
why?
you
Okay, go ahead.
repeat the question?
So here I said that at the start of the example that when you run, let's say you want to run this example on your computer. So first run the consumer process, right? Not the producer process. Why? Okay, there is a text. So that the buffer mailbox is created before a message is sent. That's correct. Yeah, because it is the consumer who is creating the mailbox, right? So if there is no mailbox, then if you launch the sender first, there will be no mailbox and it will not be able, your even your MQ open system call will fail because you are specifying, okay, this is the name of the mailbox and open it, but that mailbox doesn't exist, right? So that's why you need to first run consumer so that it creates the mailbox, and when you send, then after that, when you launch this producer, so it will be successful to access the mailbox. Okay, so this is makefile, which you can use if you want to, and actually I will encourage you to run it on your, run the example on your machine. Okay. Uh, Now, remember that we were talking about threads and concurrency topic, and then I realized that I didn't complete the discussion of interprocess communication. So we had to go back to that topic, but now we are done with that, and we can go back to threads and concurrency. So, uh, but let me give you a quick recap what we were talking about. So we said that what are threads? We said that threads are basically a sequence of execution, and what we do is like we can if we have multiple threads in a process, so we can allocate we can run them on different cores at the same time, and in this way we can speed up the execution of the process as compared to the case where we had a single threaded process, right? Then we talked about the challenges of multi-threaded programming. So we need to like partition the data, we need to find the task, and then we need to run the task on different cores, and so on and so forth, right? But the question, here is that if we want to build a multi-threaded process, it's mean that we need support, which basically mean we need mechanisms to implement threads, right? So that support or that mechanism, where are we going to implement it? Uh, so is that support provided at user level, or is it at the kernel level? What does it mean in a little bit more detail? So providing support for multi-threading basically mean that to provide mechanisms to create threads, to the to put threads to do the context switching between threads. Like for example, if you have a process, let's say process A, and it has four threads, thread 1, thread 2, thread 3, and thread 4, and you have only one core. So providing the support for multi-threading mean providing the mechanism to create these four threads, thread 1, 2, 3, and 4, providing the mechanisms to terminate the threads, providing the mechanism, like if you have single core and four threads, so how to do the context switching, like where you are running thread 1 on the core on that single core, but then after some time, as a result of some event or as a result of some decision, you kick out the thread one and you start running the thread two. So we need the mechanism which makes this possible, right? But the question is that this mechanism, this support for implementing the threads, like for creating the threads, terminating the threads, doing the context switching, maintaining all the metadata which is needed for running each thread. Remember when we talked about thread, started talking about thread for the first time, we said like if we have two threads belonging to the same process, they will share some items or some component of the address space. For example, they will share the code segment, they will share the data segment, they will share the heap, but they will not share the stack, they will not share the registers, they will not share the program counter, right? So if they do not share the program counter and stack and local registers, then it's mean that we also need to keep track of this content of the stack, the content of the program counter, and the look and the general purpose register for each thread. Then then who is going to be responsible for that, right? So and Okay, so I think enough context for this topic, right? So I think now you understand what we mean by threading support, right? So it's mean the mechanism for creating, terminating, context switching, maintaining the metadata for each thread, right? So should this threading support, uh, for example, thread table, thread scheduling, etc., be implemented at user level or kernel level, right? So even it is implied in the question that there are two options. Either we can implement the threading support at the user level or the kernel level. Let's say if we decide to use it, okay, before I go ahead, sorry, uh, these these couple of slides, they are, what's happening? Sorry. So these slides, they are based on section 2.2.4 to 2.2.6 of Modern Operating System, fourth edition by Andrew Tannenbaum. So this is not our, the textbook which we are following, but this book is also like you can go and read these sections. Okay, so okay. So let's say we decide to implement the threading support at the user level, right? So for example, in form of a runtime library. So if we want to implement at user level in form of runtime library, then it has certain advantages, right? But before we talk about that, why we are saying that we need to implement it as a library, like so because a library it will provide you all the functions which you need to create, terminate, and wait on threads. Actually, what you do in any library is that you put all the code which is common and which is like frequently needed uh, for doing some task. For example, if you are saying that okay, I will implement the support at the user level, so every time you create a thread, you will run some code, right? You will need to run some code which will actually achieve the creation of a thread. And similarly, whenever you need to terminate a thread, you will again run some code which you will need to achieve the operation of thread termination. So what you do in the library that you put these functions, all of these functions in the library, and anytime a process need to create a thread, it will simply make a function call to that library. And this library will also provide you the algorithms for scheduling the threads. So it will not be like every process will have to implement the scheduling algorithm again and again. So if you have these algorithms available in the library, the processes which are creating the threads, they can then definitely they need to schedule the threads, so they can simply make use of those algorithms. And also uh, instead that we put the burden on the processes to create to maintain the thread table, a library will be responsible. So actually, the library makes the life easier, right? Remember, we are saying that we are going to implement the threading sport on the user level. So we want to minimize the burden which we put on the user programmer to manage the threads, right? And how we do that by putting all the commonly used code in form of function in a library, and now every time when a user level code need to use them, it simply makes the function calls. So it does all these things like creation, termination, waiting on threads, scheduling of the threads, maintaining the thread table. We will see what is the thread table, and handling the thread switching, which basically mean is like context switching between two threads. Remember, context switching is a concept which is applicable to both context switching between processes and context switching between threads. Okay. So when you implement the support for multi-threading at the user level, so this is how it looks conceptually. So you have user space and the kernel space. So in the user space, you have the user level processes, and each process here is indicated by this circle. Within each process, you have multiple threads, right? And then for each process, the runtime system, it will actually maintain a thread table. So this runtime system is basically that runtime library, right? And that runtime library will be like, as I said, it will be responsible for creating, terminating, scheduling, and context switching threads. And in order to do that, it needs to maintain a thread table, right? Which gives all the metadata about the thread. And when we say metadata, it's mean the stack information, the program counter, the general purpose registers, right? And other than that, in the kernel space, you still have the process table. So this is same as like even if you have single threaded process, your kernel always maintain a process table, so it will still be there. So irrespective of whether your processes are multi-threaded or single threaded. The other thing is like when you are implementing the threading support at the user level, your kernel is unaware of user level threads, and it still treats each user process as a single threaded process. So these threads exist, but they are not visible to the kernel, and kernel still thinks or still views the process as a single thread, right? From the perspective of the kernel, those threads do not exist at all, right? Because it still treats each process as a single thread. So other thing is that one thread table is maintained per process, and it is maintained by the runtime system, which is basically the library. And each entry in the thread table, it holds the thread specific properties, for example, PC registers and stack pointer. So process table is maintained by the kernel, and user level library, it library calls to create, terminate, and schedule threads. So basically, whenever you need to create a new thread in the process code, you will make a library call, for example, create, which will create a new thread, terminate will terminate an existing thread, and schedule threads when to like context switch between two threads of the same process. So user level thread scheduling, a thread must invoke a function, for example, thread yield to voluntarily release the CPU. What does it mean? So remember that in order to run a thread, you need a core, right? So you run a thread on a core. So since you are doing the user level threading, so what happens? So let's say this is your core and a thread is running on this core. So there is no mechanism uh, which allows uh, which we can use to kick out a thread. Let's say you have two threads of the same process, so there is no mechanism which we can use uh, to kick out a thread of one process and allow another thread of the same process to run on the core. Why? Because kicking out basically means scheduling threads, right? And who is responsible for scheduling threads? Our kernel or operating system, right? But when we are implementing threading support at the user level, kernel doesn't see these threads within a process. It still sees a process as a single threaded process, right? So it is not aware of these multiple user level threads. So it will not, how to say, since it thinks that there is only a single thread, it will not do the context switching between multiple user threads of the same application. That's why a thread which is running on the core, it needs to voluntarily call the thread yield, which basically will tell the library that okay, this thread wants to release the core, and now you can put another thread of the same process to run on the core. So when thread yield is invoked, so what happens is that it will store the information of the calling thread in the thread table. So let's say this is thread one, and it was running on the core. Now, when it makes the call thread yield, so its information is stored in this thread table here, and then your runtime library will find another thread which is ready to run, right? Maybe let's say thread 2 is ready to run, right? And it will load its information from the thread table, which is basically its values for PC register, PC local general purpose register and stack pointer, and then starts executing that thread 2, right? Remember, you don't need the system level privilege to read these registers. PC register, PC general purpose register or stack pointer. You don't need uh, uh, OS privilege to do that. So it means that user level implementation of threading support allows concurrent execution of threads, but not the parallel execution. Why? Because only one thread from a process can run on a core at a time. Not two threads at the same time. Two threads of the same process can run on two different cores at the same time, right? So the concurrent execution is possible, but not the parallel execution. Remember, there is a difference between concurrency and parallel execution, right? Also, remember that kernel still sees each process as a single threaded core, and hence it allows only one thread from a process to run at a time. So it is not possible, since kernel sees only each process as a single thread, it allows only one thread from a user process to run at a time. So parallel execution of two threads from the same process is not possible when you implement the threading support at the user level. Okay. Let me stop here because we are running out of time, right? Do you have any questions? No? Okay, if no questions, then I just have uh, one announcement here. Actually, today, Module B of Project 1 was due to be released. Uh, I will release it tomorrow. My morning time and yeah, on your side it will be not morning. Okay. So,
Also,
but it will be released tomorrow. Yeah, go ahead.
sorry about that. I saw that someone also asked when we'll be getting our midterms back.
Okay, so please read the announcement which TA has made. She has set the date and the timing. You can go to our office and make objections. You can have a look at your papers. I will not give you back to them, back to you,
Gotcha.
but you will have that opportunity to look at your grading.
Okay. Thank you.
Okay, welcome.
I have another question.
Yeah, go ahead.
On the Canvas page for the assignment, it says that the submission will count towards all the members of the group. Does that mean that there's got to be only one submission for each member, or does everybody in the group have to submit the same?
Okay, here's the thing. Now, this is the first time I'm using Canvas for group assignments, so I applied the settings assuming that those settings will work and they will expect the students of the same group to make only one submission. But if that is not the case, if like it is not, if it is asking you, if it is allowing you to submit more than one version or more than one copy, then go ahead and all the members of the same group can submit individually. However, I expect that two submissions of the students from the same group are exact copies of each other, because you were asked to work together, right? And you will be then graded, how to say, at the group level, not on the individual level. Okay. Did I
Right,
answer
thank
your question?
you. Yes.
Okay. If we submit for our whole group, how should we name the file? I noticed the instruction said to user ID and name, but if we submit one, how should we name it? Okay. You can put the you can put name and AGI ID of the both students in the group. Any other thing? No? Okay. If not, then I'm ending the meeting, and that's it for now. And then see you on Thursday. Thank you. Have a good day.